So hello everybody, welcome to this important series of constraint motion. So we are dealing with the second problem of constraint motion, and this is the problem where we need to establish a relation between u and v for this block of mass m. The mass m is irrelevant over here in this problem, and we need to establish a relation for these two fixed pulleys. If the two free ends are moving with a velocity u, we need to determine v when these angles with the vertical are theta. So I will be using again two aspects to solve this. First of all, I am teaching you the logic why we are doing this, and this video is going to be very important because we will be using this logic every time in the next coming problems. So one logic to solve this problem is to establish a constraint relation using again a Pythagoras theorem, where we can mention the distances between the two pulleys, the length of these two strings, and then the way it is rising up, which is obviously a long version of the problem. And there is a shorter way. So I'm dealing with the shorter way right now in this problem. So to begin with this, let us understand a simple pulley system. So if we consider a simple pulley system, so we can say we have a fixed support, and from the fixed support we have a fixed pulley attached, and from the fixed pulley we have two masses, one on the left hand side and the another on the right hand side, where this block is block A and the another one is block B. So this is block A and this is block B. For convenience, you can consider the mass as 1 kg, 2 kg, but it is again not needed for the logic which we are trying to understand. So over here, if we use basic understanding, so we can say that initially both the blocks are at the same horizontal level. So they are at the same horizontal level. Now on being released, so if mass of block A is greater than mass of block B, then block A is going to move down by a certain distance. Let us say distance XA, and while moving down by this certain distance XA, it is going to acquire some velocity. Now since the length of the string which is connecting the block A and block B is constant, so with block A going down, the block B must rise by a equal distance in the another direction to keep the length of the string constant. So over here we can definitely say that after this instant of time, we will have block A at this position and we will have block B at this position, where displacement of A and B are same, and hence over here we can say that since displacement of A is equal to displacement of B, so we can say on differentiating with respect to time, the speed of A or the velocity of A which is in the downward direction is equal to velocity of B which is in the upward direction. And again on differentiating with respect to time, we can say that the magnitude of acceleration of A which is in the downward direction is equal to magnitude of acceleration of B which is in the upward direction. So we have established this quite easily, but this is not something which I intend to teach over here. So the idea is that when A is moving down, it is because of a gravitational force MAG in the downward direction, and when this block will try to move in the downward direction, a tension force will be developed in this string, and gradually this tension force will be transmitted to the block B, and then the weight of the block B will come into play. If the two masses would be equal to each other, then they will balance the forces and the system will stay in equilibrium. Now since mass A is greater than mass B, so we can say that the gravity is doing more work on block A moving in the downward direction, and then the block B is going in the upward direction and the gravity is doing negative work. So if we are looking at from the work energy aspect, so we can say work done by gravity on A is going to be plus mass of A G displacement of A which is also displacement of B. So for XA equal to XB, we are just using X over here for the time being. If we calculate work done by gravity on block B, so we can calculate that the work done by gravity on block B is negative. It is minus of mbg into x. So if I calculate total work done by gravity on the system, so total work done by gravity on the system, which is comprising of A and B, then it is equal to ma minus mb g into x. And this work done is transformed into the kinetic energy of the system, which can be written as half ma va square half mb vb square, where va and vb are equal to each other. Over here, another interesting fact which we have missing out is work done by tensional force. This is the key, work done by tensional force, to establish the constraint relation. So over here, since tensional force is an example of internal force, so over here I can say that as A is moving in the downward direction, so at an instant of time the velocity of A is v, A in the downward direction, and the velocity of B at an instant of time is vb in the upward direction. Now if we calculate the work done or power for a certain span of time, then I can say that the tension and velocities are in the opposite direction. And if you know the formula for power, power is equal to F dot V. So F and V are in the opposite direction, and for a small duration of time, say delta t, we can say T VA times delta D is in the negative direction, and then plus T VB delta T is in the upward direction. And since all of this is taking place in the same interval of time delta T, and tensional force is an example of internal force which will not be doing any work at all, so we can say that we can equate this to 0. So if we equate work done by tensional force or internal force to be equal to 0 for a system, then we can easily establish a constraint relation that TVA is equal to TVB, and from here we can say VA equal to VB in magnitude. So this is the idea which I will be using to solve the problem which will be coming next, that we will be using tensional force and we will be using dot product of T dot V. So if there is an angle between T and V, then we will take a dot product between T and V to write the expression. So if we go back to the problem which we have, so now this problem will look much easier. So over here if I say that the tension in this part of the string is T, and since it is the same string, so over here also the tension will be T. On this end tension will be T, which is again tension T on this side. So now over here I can say that from the aspect of power, or considering the fact that the work done by internal forces is 0, so we can solve this problem in one single step. So T and U are in the opposite direction, so we can write minus TU. For the right hand side part, again we will be writing minus TU, and this is equal to, so T is in this direction, the block A is rising in the upward direction with a certain velocity V, and they are making an angle theta with each other, so we can say TV cos theta, and we are doing this twice, so twice of TV cos theta, and therefore over here we can say here it must be a positive sign, and then this entire work done aspect is equated to 0. So therefore from here we can say 2Tu is equal to 2TV cos theta, and 2T cancelled out, so we can write V as U upon cos theta. So this is the simple idea on which we can solve the problem, that V is equal to U upon cos theta, where we have used the idea that work done by internal forces on a system is equal to 0, and I will be using this in all the coming problems where the tension is involved. So we will just be writing T and V expression, or T and A expression for that matter, because if we differentiate this expression, then we can definitely write it as AA and AB. So you can easily write this equation, and this is the logic which we are using to solve the problem which will be coming next. So this was the second problem in the constraint motion series. Let us go for the next problem, which will be the third problem of the series.